the large language model space because as someone interested in machine learning and systems, I found LLMs really a great intersection where I can learn about both. So today we're going to start off with why this is training. So why should we talk about this? We're going to do kind of high-level overview of the algorithms. Then we're going to talk about different architecture options for circuit training, and we're going to end up with some more practical suggestions about frameworks because LLMs and circuit training is a flourishing field, so we have a lot of different options. So circuit training kind of kicked off with LLMs. So we had circuit training before. We used data parallel training, computer vision models. I'm going to talk about it later. But where it really took off is when the models were so big, you can't put them in a single GPU. And then you have to go across them. And then the tricky part is to use machine learning and to engineering knowledge because you have to scale up, you need to have not only compute but communication efficiency. So you have to think about much more. So as you can see, like only in the last few years, from sort of like 2019 through the current, it kind of took off. And today we're talking about 500 billion models. And I think that's very interesting and very revolutionary. And that's what also kind of drove the end of the revolution in chatbots like ChatGPT. And we're seeing that in other fields, for example, generated models or even computer vision. So, okay, now we're going to start with kind of the overview of algorithms. So initially we had data parallel. And I think that the best way to explain it is to mirror it with model parallelism. So data parallelism is when you have a model that fits on a single device, like YOLO or SSD, and you want to train it faster. And then what you do is you partition the data and you feed it to multiple items. Right? And so the issue here is that, yeah, okay, it's simple. It doesn't need as much communication as other parallelism techniques, model parallelism. But what you can see is that we kind of duplicate the data because we just manually replicate it across the workers. So the next idea to kind of make data parallelism more efficient was FSD, so fully sharded data parallel. And here, with data parallel, we essentially have just all the views across everything. Here, because with fully sharded data parallel, we are kind of splitting the models, so we're partitioning the model, not just replicating it, and then at different points in time, you just have to gather specific part of the model on all machines and do the same data parallelism. So you fit the data partition to each machine. And so, at least for me, FSDP was kind of confusing. To watch this visualization, which is very nice, and it makes FSDP extremely simple. Cool. Yeah, so what do you think compared to data parallelism when we, have several replicas and then we take a batch, train on each replica, and then kind of average through all the replicas versus this? What has more communication? Which algorithm? Is it data parallelism or FSDP? Anyone? Just guess. Which which algorithm has more communication? FSDP or data parallelism that we talked before?
Yeah, the model.
Sorry?
The model parallel.
Data or FSDP? Yeah, cool. Yeah, so that's kind of the common trade-off, right? You can have kind of more computational efficient algorithm, but you need to do more communication because here, for example, we don't replicate the model on each node, so we have to communicate that model. We can, do things faster. We can train bigger models, but we have to do more communication. So FSDP is kind of in between data and model parallelism. And the next step, of course, is model parallelism. And with model parallelism, the idea is that we partition the model across the nodes. And here we're getting really communicationally hard algorithms, because here you don't have any replication. You essentially you take a model and you partition it across GPUs. And here you have to communicate on forward and backward paths, just as we do with FSDP. But the good thing is that with model parallelism, we can do essentially tensor parallelism. So we can take a layer of transformer, for example, and split it across multiple GPUs. Or what we can do is do pipeline parallelism. And that means that we assign different layers to different GPUs. And with pipeline parallelism, the interesting branch of research is how to schedule those chunks across multiple GPUs, because now we have to understand that for each token, for each data point, this data point has to travel across different devices, because each device holds its own partition of the model. And here on the first diagram, we have the naive implementation, but the issue is that the blue ones are forward pass, the green ones are backward pass. But the issue is that there's what's called bubble in between forward and backward pass, and that's where GPUs are idle. And as MLOps engineers, we want to be really cost effective, so we want to use our GPUs all the time if possible. So the research here goes into how to minimize that bubble time. And for example, what NVIDIA did below is you have interleaved schedules. So it's not just that you go forward, 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 and then backward, 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 but you interleave the forward and backward pass. And by that, as you can see, you have smaller gap between forward and backward passes. And that's essentially minimizing the bubble, which means maximizing GPU usage. So data, FSDP, and model parallelisms are kind of the main ways to do distributed training. Kind of the newer research is more about how those three modes of distributed training interact. So for example, how do we partition the model if we're doing data pipeline and tensor parallelism? Because for example, you want to keep tensor parallelism between one node, because tensor parallelism is the most communication-intensive algorithm. Now, some other interesting techniques are, for example, sequence. So sequence parallelism, because we want to have wide context window to train LLMs, right? So what we can do is we can split sequence across multiple, for example, replicas. And then what's called ring self-attention, where you do essentially all reduce, but you do it in a ring style. So that way you partition the sequence, but the model thinks it's one long sequence because you send around keys and values in attention, for example. Yeah, so some further optimizations are, I think, very interesting because they're usually between engineering and machine learning. So for example, with quantization, we can do mixed precision, where we do some part of computation in FP32 and some part of the model are in FP16, for example. Then another interesting technique is LLM8, because what they found out is that as we scale transformers, we see emergence of outliers in different embeddings vectors. And the issue with quantization is, so with quantization, we're essentially going from
32-bit representation of floating point to 16-bit representation. And when you kind of downcast the data type, the challenge is that with outliers, you're getting huge error. And what you can do here is that you can, LLM8 algorithm kind of leaves the outliers in higher precision and does lower precision computation with other values which are in kind of the normal range. Then there are things like knowledge distillation when we take bigger model and distill it into a smaller model. And that's pretty interesting for transformers because you have this pre-training transfer learning regimes. Then we do pruning, for example. And the next kind of also very new thing which was discovered this summer is flash attention, which essentially takes into account GPU memory hierarchy because not all deep learning is compute bound. Some operations like softmax, for example, are bound by memory because it's not that you have to compute huge matrices. The issue is that with softmax, you have to do a lot of pointwise computation. And then you have to retrieve those values from, for example, L1 or L2 caches to registers. And that's a big bottleneck sometimes. And then the two things worth mentioning is activation checkpointing, where you recompute in backward pass instead of saving it. And that again, like for example, before we were talking about trade-offs between replication and less communication versus partitioning and more communication. Activation checkpointing is another example of trade-offs in distributed training because with activation checkpointing, we're not saving values from forward backward pass, but we're rather recomputing them. So we're essentially saying we're going to sacrifice some computation, so we're going to do more computation. But by doing that, we can get more memory, so we can fit larger models in less GPUs essentially. And then offloading is kind of similar. You have to communicate between GPUs and CPUs, or GPUs and some sort of NVMe storage. And by again doing some more communication, you can fit more. You can save on communication somewhere else. So I'm going to present kind of two architectures on how you can run distributed training. So distributed training jobs are usually highly coupled because that means that you're training them on a lot of nodes. If I don't know, train GPT-3 on 32 nodes, and I only get one node, there's nothing I could do because I need the whole nodes to partition the model across the GPUs because it's just not fitting in one GPU. So yeah, so that means it's highly coupled and usually do batch jobs. So we're not talking about deployment where you deploy real-time, I don't know, API or something like that. You're deploying a batch job and you can leave it over the weekend or with LLMs over a few months or something like that. So Slurm is kind of I'd say, old school HPC scheduler. And it's made for those highly coupled, tightly coupled batch jobs. Because Slurm is kind of made on MPI, which is how a lot of like GPU to GPU communication can also be done. And if we compare it to Kubernetes, it has much less features. But in some cases, that's okay, because there's less complexity, there's less things that can break. So the bottom line is, if you have tightly coupled batch jobs and nothing else, so for example, if you're a research team or a research lab that doesn't have to deploy like APIs or something like that, Slurm can actually be a great solution. And then you also have Pixies and Inroot, which give you container support. So you can run containers as you do in Kubernetes, but it's easily to run them in this tightly coupled batch fashion. Then the next option is obviously Kubernetes. So it's a bit more complex. It has a bit more features. The nice thing is that once you start learning it, usually it's pretty interesting. It has a rich ecosystem. It has just a lot of people around it. But the challenge for distributed training is, again, that you have these tightly coupled jobs. So you want to deploy, for example, deployment or replica set, and you want all of the replicas to get deployed or none of them. So if only 1 out of 10 replicas gets deployed, again, you're wasting your resources. And to do so, I know that there are at least 2 ways to work around it. The first one is there is a project called Q. And you can think Q as it's an operator, it's sitting in front of the Cube API. And you're kind of limited with what kind of objects you're deploying. Specifically, you can't reuse operators. And with Kubernetes, there's a training operator from Kubeflow, which helps you with distributed training because it helps you with essentially assigning ranks across workers. So the second solution is actually what at least supposedly OpenAPI uses, which is the creator of ChatGPT, and it's co-scheduler plugin. The good thing about this is that it's a scheduler plugin, so it's much more flexible with respect to the object types that you're deploying. The downside here, at least in my opinion, is that this plugin is made for kind of, when I was talking about slurm, I was talking that there are 2 things. First, tightly coupled jobs, and then you can do batch queue scheduling. And with scheduler plugin, you get the tightly coupled aspect. As far as queue scheduling, I think that the first project, Q, is much more suitable because co-scheduler doesn't really have this concept very well defined. And I'm sure that it's gonna get better every year. But yeah, those are kind of the upsides and downsides of each approach. So the last part is few frameworks to try distributed training in real life. So the first framework that I know of is PyTorch, because PyTorch has really great inbuilt support. So you have data parallelism through DDP, and you have FSDP, which is fully shared data parallel. There's also other options like gpipe and a lot of open source projects, but I would say DDP and FSDP are kind of the most well-known for distributed training. The second one is Megatron, and actually the Megatron team wrote a lot of very influential papers. Some of them were sourced for this talk. And here you again have this a lot of different projects. So you have Megatron LM, which is more research focused, and you have Nemo, and both are kind of managed by NVIDIA. But Nemo is kind of meant for a wider audience. So you have a lot of things kind of nicely wrapped. So it's much easier to just run GPT-3 with Nemo than Megatron LM, for example. The second one is Megatron Deep Suite, which has this Deep Suite integration. And for example, Deep Suite was made by Microsoft, and Microsoft also kind of initially developed this FSDP algorithm before known as Zero, so Zero Redundancy Optimizer. The third one is this big science fork. So here we have, for example, Hugging Face, who are working in this repository. And I think, with big science, it's much more kind of flat hierarchy. There's a lot of people working together through open source, through this big science initiative. And then maybe the last point that I'd like to make is that out of those different frameworks, even though Megatron is kind of more complex, it's more engaged, the good thing is that it has really nice integration with, for example, TensorBoard. So we can get not only ML metrics like accuracy, but you can also get different latencies, which is very important. So you can get latencies for different communication operations, like all reduce, all gather, reduce scatter that we saw before. And yeah, the third one, which is also kind of worth mentioning, is Deep Suite, which is, I think, probably the library that started it all, that started a lot of distributed training projects and discussion. And here you have Zero, pipeline parallel and mixture of experts. And we were Zero and FSDP are kind of the same. There are some small differences, but FSDP was sort of inspired by Zero. And yeah, then my last point would be that with LLMs, usually we can deploy, I don't know, Prometheus and monitor GPU usage, or we can monitor, for example, InfiniBand or EFA, so we can monitor how much communication happens. But with LLMs, the performance is kind of so important that tools like Prometheus are just too much high level. So to get something more low level, what you can use is NVIDIA Insights, and that's how essentially it looks. And you can of course zoom in, and there are also some statistics, stuff like that. But the idea is that you get essentially time series on millisecond scale, and you can see when different, for example, CUDA kernels are triggered, when different nickel operations are happening. And then what you can use is NVTX markers, and you can annotate your code with NVTX markers. And that means that you can annotate your forward pass, and you're going to see all the CUDA kernels and nickel operations that happen during during forward pass, for example. And the same goes for optimizer step or backward pass. So it really allows you to see what's happening in your code. And that's not just useful for distributed training, but also if you wanna really optimize, for example, inference, you can also look at this, and you can see that there are some kernels that are very unoptimized, and you can do some kernel fusion or something like that. So it's more low level and more engaged, but it gives you really all the information you need, essentially. Thanks.
Brilliant. Yeah, thank you very much for that, Uroš. As you've seen from that, pushing not only the bounds of machine learning training, but you saw the video at the beginning, the bounds of what can be done with a PowerPoint animation as well. So yeah, if we got questions for Uroš, what we'll do is just put your hand up and I'll come to you. If you could say it into the mic, that'd be great, because then people online can hear. And if you're online, put it in the chat and I'll read it out in a second. So yeah, any questions? No one? Yeah, there we go.
So a lot of the techniques that you showed seem to be designed for sort of really pushing the state of the art in what can be trained. I think there's some evidence, or maybe some reasons to believe that, especially if you're doing more specialized tasks, that large language models at much smaller scales, like small scales, like 60 billion parameters and below, maybe are sufficient or even optimal. So how easy would you say it is with all this tech to train one of those things? Is that still extremely difficult? Or considering it's like 2 orders of magnitude or so below the state of the largest models, how easy is it to become to train like those sorts of sized models?
Yeah, so even with 60 billions, you have to go probably multi-node. Maybe you can do it within single node. So it is a bit easier. I think what's also the big challenge with bigger models, even 60 billion, is that you also, even with the same amount of data, it's going to take longer. And then you also have to start thinking about, you have all those nodes, you have to start thinking about different GPU failures and the different parts of the system failing. So I think that it's sort of logarithmic, kind of with respect to model size.
Great. Any more questions? Yep.
Hi, I have a similar question. I think it's fascinating to see you show the details. But as a practitioner, we have a quite big, machine learning engineer team. More than 10 machine learning engineer, and over 20 data scientists. We barely train such a big model. Also, based on the AWS or Azure, they also do training, show how easy using their platform to train and also issue, how we can do this. But just in industry, it's simply not just consider the cost, and also the previous question mentioned how difficult to train the model, and also how many out-of-the-box API available. Basically, if you call the API, it's probably not just save your time and money, also it's probably perform better than the model you train. So, what's your comments based on the observation I just mentioned? Do we really, as a practitioner, need to spend money and train the model, or rather just call API? Yeah, I think that's just.
Yeah. So what's my opinion, and what I think is also kind of divided opinion in the industry is that there are some such thing called foundational models, stuff that is behind API from biggest cloud providers, etc. But what we're seeing currently is that kind of some small to mid-sized companies are kind of ahead of the time, for example. So we're seeing a lot of startups who start training models from ground up, or even if you have to do fine-tuning on models like that, you still need to do distributed training. Now you can use managed service, but I don't know, just some people like to do it on their own. I think that, there is very small amount of companies that have the money and the talent to pull it off. But I have seen, companies with the size of 20 to 30 people tackling things like that on their own, betting that they're gonna outplay other players. So, but yeah, I think that generally you don't need to understand what's going on under the hood. But even if you invoke an API, they're gonna say, okay, we can do data distributed training, like with SageMaker. Even though we have an API that kind of handles a lot of model training, you still need to know that. But yeah, there are other things like OpenAI API where you don't need to have any idea. So yeah, I think that it's nice to just understand on a high level what data parallelism means, but yeah, most of the companies don't really need to understand how to manage everything from ground up.
Any further questions from the audience? I think that last one was very good. Yeah, go on.
Thank you. So I can see a pattern here on the ML. Is there any relevance with the Lucene-based search, if you have heard about?
Sorry, what?
Lucene. It's a library which facilitates indexing of text, whatever supply.
Neural search.
Lucene, Apache's Lucene library.
Oh, sorry.
Yeah, that's fine. So my another question is, we are talking about large data sets here. Mm-hmm. If I have to start very simply with 10 parameters, with, for example, if I want to train my resume, mm-hmm. So I can answer for any further resumes. So is there any way to get started?
Yeah, I think that, starting with one of those, for example, with DeepSuite, or just plain PyTorch, like PyTorch GDP. The thing is, if you just do data parallel, you have to worry a lot less about, because you don't have to spin up hundreds of GPUs. You just spin up one EC2 instance, and on one EC2 instance, you have multiple GPUs. You can have multiple replicas. And I think that, for example, PyTorch has a lot of blocks that are easy to follow along, and DeepSuite has a really good documentation. So I would go with either one of those.
Great, thank you.
That's actually prompted me to ask a question about, so yeah, I was thinking about it from kind of my perspective, which is I don't do much training. And if I did, I would just kind of go, throw a bigger GPU at it. And obviously eventually you hit a limit in terms of cost and what you can actually do on a single GPU. But are there cost efficient ways of saying, if you've got something that could run on a state-of-the-art GPU, but you could run it distributed across a bunch of very cheap GPUs, Does that often work out better? Are there these kind of like cost trade-offs you could do?
Yeah, I mean, you can essentially have smaller amount of GPUs, but it will take longer, for example, because you can't distribute data partitions across multiple GPUs, right? Instead of
Yeah, sorry, what I meant was
yeah,
like,
that's really hard to do.
Rent 100
There is no
GPUs.
free lunch, essentially, more or less, unless you figure out new algorithm that's just like, superior from computation point of view. So unfortunately, no. Yeah, it is, as you pointed out, it is capital heavy. You need a lot of computational power to pull it off. But either also for transfer learning, or if you just want to do inference, if you want to do inference on GPT-3, you still have to go somewhat distributed.
Okay, cool. In fact, we're gonna hear about that in a minute. There we go. Paul giving me a cheers from the back. Yeah, we're going to talk about GPU inference on large models after the break. So let's have one more round of applause for Uroš. What we do is we'll have 5 or 10 minutes. You can go to the loo, if there are drinks left, go and grab one. There's a little bit of food in there, I can see. Have a quick chat amongst yourselves while we get set up, and then we'll start again in 10 minutes or so. Okay, well, welcome back. What was I going to say? Oh yeah. Okay, so two important pieces of information. The first is that the next one of these events, if you want to bookmark your diary already, is going to be on the 28th of March. So these are every 2 months. By the way, if you're new here, do this every 2 months. Yeah, the next one will be on the 28th of March. So put a little bit more than 2 months' time, but it's hard to find this venue on Tuesday evenings. And then the second one, which kind of relates to that, but maybe on a longer term, is that I'm always looking for interesting talks, right? So actually, I've got them lined up for March. But if you want to speak in the future beyond that, and if you think you're doing something interesting in your work, or you have an interesting like personal story to share, please let me know. This is a very open and informal space. If you haven't presented before, no one's going to bite your head off. I'll help coach you a bit if you need it. So yeah, please do come and let me know. It'd be great to hear all of your stories. And with that, I'm going to hand over to Paul, who's going to talk to us about GPU inference to kind of complete the GPU spectrum for the day. So big round of applause for Paul.
Hello. Can you hear me? Yeah, good. Hi, I'm Paul. I'm CEO and co-founder of Mystic. We were previously called Neuro.ai. We started in kind of beginning of 2019. Originally, we were a hardware company, and now we're a full software infrastructure company for machine learning. And what I'm going to be talking about today is a lot of the research we've done and additional kind of software engineering things, specifically for serverless GPU inference. So yeah, as I said early on, we started off as a hardware company. So top left is an amazing like little ad thing that we made a while ago with my dog. But my original research that I was doing at university was in analog computation of machine learning. And we then started the company based on a novel processor design for machine learning. Doing hardware as a startup is really difficult. It sucks. It's very difficult to raise money. And yeah, there are a lot of other AI hardware companies doing it. So we were trying to think about ways that we could add the same value as better machine learning hardware could, but purely through a software perspective that didn't have the upfront capital cost, really long lead times, things like that hardware does. So we came up with an idea to get users to send us their code, their machine learning models, in a serialized form. We would then handle all of the hardware communication, hopefully, to then test things on our own hardware, and then just send them the result back. So from that, what we ended up with is this nice little server rack that we had here in our office at the time, where we would take in API requests from a user. They could serialize models, send them, and then we'd complete the chain just doing regular inference for them. So that's kind of originally where we started off. Again, as we were called Neuro there with a different logo. So where we ended up then was we were trying to talk to people about the value of just augmenting away, so this was in 2019, 2020 at the time, augmenting away all of the software difficulties of running machine learning models. So we started talking to them, and then they were like, if you could not have us run everything in K8s, where they were spending ages trying to set these things up. They're really brittle, super expensive to run, yada, 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 as I know a lot of you will know. They were like, okay, this sounds great. So then we started investigating what kind of an ideal production setup would look like that was bare bones, that would allow people to do just purely inference, just straight out of the box. And we looked at this from a hardware and software perspective, because the two are very, very, very interconnected to us. So what we found is typically they would have a user that could be an internal service even, or an external user that would want to do something with machine learning that would propagate through to some kind of ingress service, typically an API or something like that, which would then propagate through the rest of the system. You'd have CPU services, databases, things like that, and then also some form of storage that would also talk to the GPUs down here, which is the really expensive bit that, as I'm sure you all know, is very difficult to set up a lot of software on and make it very effective to run. You might have some storage unit here to make loading storage faster. Storage cache, Squid cache is very commonly used here when you have high bandwidth interconnects, things like that. So typically, what we found people were doing, and I know it's still very common as well, is the majority of this end after the user, excluding storage, was running on some form of Kubernetes or scalable infrastructure. which is very reasonable, manages containers and things like that, but there were a lot of issues with doing that. So that's when the whole world of MLOps obviously came about, where there were a lot of specialist software for running Kubernetes specifically oriented for machine learning. We found, though, that people still struggled in companies to use a lot of these tools as they were so focused on running specifically Kubernetes, where you required a lot of experience and a lot of knowledge about K8s to run any of these applications. So our goal was to make something that allowed users to get scalable infrastructure without needing all of that latter MLOps knowledge. A lot of tools, even like Kubeflow and things like that, you still require a lot of K8s knowledge. They run very differently on your local system to running in production, very brittle. There's just a whole host of issues. So this is the typical kind of stack that I was talking about. You'll have some form of code, be it in R, Python, typically Python at the moment. You'll Dockerize it somehow. You'll put all of your dependencies on there, and then you'll deploy it somewhere, typically on K8s. That's the regular flow that we saw. So the first way that we set out to change some of this stack to make it easier for data scientists who are running these things was to allow people to do everything they needed explicitly in Python, to not come out from there. So we created a library called Python, mostly for internal use at the time, which we're now kind of starting to open source and put out there to the world, but it's mostly been internal use up until now. So you can check out the repo there. This is a nice little code snippet. But the example we see on the left-hand side is creating a pipeline, as we call it. Pipeline.ai is the product now, for GPT Neo. So GPT Neo is an open source model created by Hetherington AI, which is like a smaller version of GPT-J, which is in turn a smaller version of GPT-3. So all of this code here, and then just at the top up there, is all that's required to create a full pipeline, as it were, to input some text and get an output generated from GPT Neo. Now, all of this code that's generated here can be serialized and sent through to our orchestration software to get immediately a full out-of-the-box scalable solution. So down here, we also created a couple of things where if you wanted, for whatever reason, to still run inside of K8s in some existing infra, or just run a single Docker container or anything like that in your local system, this still provides a tool to generate all of those Docker files for you. So ultimately, all you have to do is just sudo docker run. Now, what I'm going to talk about a little bit more now is some research on, now that we've got all of those serialized pipelines, let's say you have thousands of them or hundreds of them that we saw was very common in enterprise use cases. So a lot of people we found will have small models, say under a gigabyte of VRAM, those kind of things, maybe a few hundred megabyte, where they would have hundreds, if not thousands of them, where they were trying to run them maybe on an on-prem setup or on a limited number of GPU resources somewhere. So now that we have all of our serialized models, what our next kind of challenge was, now that we have all of these models, how do we effectively load balance and handle all of that compute on loads of GPUs? So because we work just purely with serialized Python code, what that means is we don't need to create a new Docker container per model. And that was the big difference between our approach to a lot of other people we've seen. So we can run 100 different variations of a model, perhaps with some different dependencies, all inside of one Docker container through virtualization of environments and things like that, meaning that one GPU can run loads and loads and loads of things, whereas normally you would have one Docker container attached to one GPU. And typically that would be inside of a cluster for one model. So there, the inefficiencies of the GPU utilization were really, really, really low, we found with a lot of people. So I don't know how many people here do the MLOps for companies they work in, but a very common thing seen is you have loads of GPUs spun up and none of them are ever being used, or the utilization of them is super, super low. So that was the main thing that we really wanted to tackle with our new architecture, was that. So because we can take these serialized models, we can do GPU sharing, meaning we can have multiple models stacked on a single GPU. So the next set of slides that I'm going to be sharing are results from all of our simulation software for trialing different number of models, pipelines we call them here, throughout a set number of GPUs. So here are just some parameters for the experiment. We're running about 500 different machine learning models here. We have a cold start time, so the initial loading time, whatever that might be for that model, minimum of 10 seconds, maximum of 20 in that range. Again, this can be very flexible. It does change optimization and things like that. GPU memory under 1 gigabyte, above 600 meg, so on and so forth, just for these experiments. So the top left-hand side here, this set of charts shows what we call the first free strategy. So if any of you are familiar with Celery, it's like a queue. Sorry, Siri. It's a queue, or it's basically just a long queue, and you'll have a bunch of GPUs listening to that queue. And then whenever a task comes in, there's a race condition to whatever GPU can pick off the queue the fastest. So that's a very, very, very common way that people would deploy machine learning models in production. So that's the first free strategy, which is what we see up here. Now, in this simulation, what we have is 100 T4 GPUs that you'll very commonly see at AWS. There's a fixed number of them, so this does not include auto-scaling in these simulations. And we can see with first free strategy for running all of this workload, we have a utilization percent of around 70% of the GPUs. So 7 out of 10, 70 out of 100 GPUs are consistently being used. And then when we do everything with our improved routing strategy, we drastically lower the utilization rate, meaning we fit significantly more models on fewer GPUs so that the number of GPUs you use is a lot less, so your AWS bill is a lot lower. And the next slide will give a few more metrics on that. Another great benefit of this is with our routing system, what we do is, based on historical data, when tasks come in from users, we use historical data of that to estimate how long new tasks will take. So when we do routing, we calculate time to compute, as it's called. So we say if one model is cached here and it's not cached there, it's probably going to compute faster on the resource where it is cached, so on and so forth. And then that can also be drawn out to heterogeneous GPU environments where you have many different compute resources. Say you have several T4s or several V100s or A100s on a cluster. This routing takes into account all of those things. So time to compute also then drastically lowers the average task time to compute a task, which is just some ML inference workload. So the great thing here is, you can see the resources here. So this is the average use in a typical A8 system where you just, K8 system where you just pick things off of Celery. So you can see here all of the resources kind of try and keep busy, which is why the utilization is high, meaning you're using lots of GPUs, which isn't good. But with our system here, it's very, very, very staggered. But we end up building queues for individual GPUs based on their compute requirements and things like that, if the model's cached there. But the best thing is here. So on the next experiment, with the same load that we had before, we've reduced on our routing system, we reduced the number of GPUs by 25%, and then we show that we can handle exactly the same workload, which is really good, because it means you don't need as many GPUs. What is also good further on from this, and I'll come on to just after, is there's a lot more that you can do just on the routing to drastically reduce the number of GPUs that you're using. So where we're going to be focusing some of our efforts on shortly is on kind of further increasing things. So it would be reasonable to say we'd probably be able to half the number of GPUs required for the same workload, in this example here. So preemptive caching. So say you have a user come on your system or an internal service that starts using a machine learning model, and it becomes very predictable. We will, ahead of time, then cache that model or pipeline, as we call it, on different GPUs so that they are ready to go, they're warm ahead of time to run the models. Preemptive auto-scaling as well. So in a similar way to that, you want to start more GPUs ahead of time instead of just listening to queue length, which is the standard way that K8 handles its auto-scaling. Better time to compute estimation, so rolling in a lot of machine learning to actually estimate how long a task will take to compute. And then further on from that is maximizing GPU memory utilization. So in our system here, it does cache things quite nicely, but we can still pack more GPUs with more models to make sure that just a few servers, a few GPUs are constantly running. because you don't want anything to be cold because you're still paying AWS, GCP, whoever for that really fat tab that racks up pretty quickly. So on top of that, what we're also going to be working on a lot more coming up is improving the quality of our library. Up until now, it has very much been an internal service that we've used. So the UX is something that we definitely need to work on, as is very common with an early stage open source library. So we're going to be working a lot on that. You can run things made in our library kind of anywhere, but we are going to be improving a lot of the ways to do auto K8s and things like that, should you want to, for whatever reason. Because one thing we definitely don't want is for people to feel like they're locked into us for whatever reason. That typically doesn't work well with engineers. So in addition to that, we focus very strongly on inference at the moment. We do have support for fine tuning and things like that, but we are trying to complete the rest of the model lifecycle. So auto fine tuning, alert system, your system goes down, letting people know, those kinds of things. And then also a lot more visibility into the production system. So how many GPUs are you using right now? A slider that allows you to opt into more expensive system that is a lot faster, or a slower system that's a lot more affordable. Things like that, we have a lot of direct control over that. So yeah, thank you very much.
Great. Yeah, thank you so much, Paul. Questions from the audience and then people online as well. Remember, put it in the chat and I'll come to it in a second.
Thanks for the talk, very interesting. My question is, I think you mentioned it briefly in the beginning, but what about the data that the clients send to you? So it can be very large amounts of data and there might be updates like constantly shooting at you. So how do you handle that?
I'm not sure quite what you mean by that, by data. So, well, there are two things that we can offer. So we have our self-serve product that utilizes our own server farm where we run everything, but our software is portable and can run anywhere. So if we need to run that on their on-prem setup or on their own cloud account, there's something that we can do. So in which case, we're compliant with GDPR or just whatever data restrictions, things like that. And then in terms of our own internal bandwidth, because we have made our own server farm, there's a lot of things we do to make data transfer very, 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 very fast. So it's like even, basic GPUs having very fast interconnects, like networking and things like that. A squid cache, like I spoke about with data. So we have our own internal S3, what is called MinIO or Minio, however people call it, which is what Amazon's S3 is based on originally, I believe. So we have our own, kind of systems that we use there with very fast uplinks to make loading very fast. And then there's even NVMEs that are physically on the system. So typically when you use a cloud provider, a lot of storage is ephemeral, meaning you load it from somewhere else and then it's networked directly to you. Which is why often when you turn a server off and on again, everything's gone with standard ephemeral storage. And then it's really expensive if you up the limit because the IOPS count and things like that. So because we run everything ourselves, again, we can run it for people, but because we run it ourselves, we can optimize a lot of those data transfer things and logistics, if that answers the question.
Other questions? Yep.
Hi, thank you for explaining. I understood from your point, like we will be having a common Docker file for all of the applications. So I want to understand like what will happen in case of failure. Like if you'll be having a common Docker file, then in case of failure, will it affect in a huge way or how it will go?
Yeah, it depends to what extent the failure is. Because you can have CUDA OOMs, for example, where you try and load more into memory than you have in CUDA are like the most annoying things that we work with. So trying to remove something from GPU memory is notoriously really difficult. So that's the most annoying failure we deal with. But there's things you can do to remove to what extent just like a system exception can kind of hurt things. It also depends on the volume of traffic. So if you have a lot of GPUs, that stuff is kind of okay if you have one GPU drop out, because we do distributed caching as well. Typically, a single model will be cached in multiple locations. So one of them falling over, another service will pick it up and say cache it somewhere else or something like that. It will make a single attempt at doing an inference process slower, for sure. But the trade-offs compared to having a more optimized system are definitely worth it in our opinion, as a failure tends to be quite rare, meaning, you'll have one failure maybe in tens of thousands of requests. So in that case, it's okay. But it is still not fun for anyone though. Yeah.
What kind of distributed GPU training do you support?
Yeah, so at the moment, none, and it's mostly because of like the client base that we've been going after. So if we were to base our day-to-day work that we do from our Discord, it's very different from like our private sales channels that we have over email. So a lot of what we get from like public other startups is, it'd be great if you had Dream Booth and things like that for fine-tuning Stable Diffusion, but that's not our target customer base, I'll put it that way. So we can do training and things like that. Fine-tuning is totally fine, but for highly distributed training is something that we don't do at the moment. And as you can see from like the last talk, for example, you have to go very low level per model to do a lot of distributed training. Torch it's okay for doing primitive distributed training, but when you're doing like multi-model, multi-GPU data parallel training over like a node of 6 or something like that, you need the user to be very expert. And I don't think a system like ours will ever be good at that, because it's just not designed to be. You're better to be running, your very own custom system. And there's like 10 people in the world that do that anyway. So yeah, yeah.
Any other questions? Yeah.
Hi. Everything was very much focused on GPUs, and to me, it seems like some of these things could also apply to CPUs. Yeah. Why is that? Or could you go into that?
Yeah. No, it's a great question. So what we see is like there are two ends of value adds that we see in terms of our product. So one is cost savings, and then the other is ease of use, hopefully, for people to do what they want to do. So in terms of the cost savings, the value add in terms of reducing number of GPUs is very clear, because we can say we can do the same amount of work with less GPUs. So there it makes total sense. But in terms of CPUs, yeah, again, super great. So the plan for the rest of our product, and a lot of kind of enterprise customers we're talking to right now, there is a big focus on CPU compute, specifically, XGBoost models, random forest, just more CPU-bound compute workloads. Or just basic, number manipulation and NumPy and stuff like that. There is definitely a huge market for that, and one that we still software like this, enabling people to step away from touching K8s in any shape or form. We just augment that. That's kind of the main value that we see to them, that their data scientists can interact with this instead of an MLOps engineer or a DevOps engineer. That's kind of what we're trying to go for there. This works fully with CPU for sure. There's like a flag on uploading pipelines to us for GPU or CPU, then amount of VRAM and things like that. Yeah, this talk was just primarily on GPU, just because it's a big research area for us as well. But yeah, can totally do that.
Cool. Any other questions from the audience? One from me was that you talked about the kind of sharing of GPUs as being one of the value adds. I know that, in GKE, you can do that already. They now have like fractions of GPUs. It may not be as sophisticated in its scheduling. Do you see that being a thing that eventually, all the cloud providers will have some sort of, GPU sharing mechanism anyway in the future?
I think they'd probably be stupid if they didn't. But the question then comes down to user experience. And the person that often we found a lot of cloud products are selling to, and not the people building machine learning things. The issue with GPU sharing and sharding and stuff like that is, so I'm familiar with like even the licenses you require to do a lot of that. So when you're breaking up a lot of GPUs, often you require, it's called an NVIDIA grid license. It costs a fortune. So you have to install a license on the machine that allows you to break up. It's existed for a very long time. Even like the old tensor-based cores, or Voltaire, sorry, like T4s, you can break them up into like 16 individual GPUs with 1 GB of VRAM each. There are a few issues with that. So firstly, it's very technical, very low level, and doing that stuff with NVIDIA is notoriously very difficult. If you are a data analyst inside of a hedge fund, trying to play around with NVIDIA drivers and grid licenses and trying to bake up the GPUs is just no bueno. So it depends what the product ends up looking like. You can definitely do those things, but as software, you can kind of do anything. I guess the question is down to the user experience and who ends up interacting with it. I think who we try and target towards is like a machine learning engineer who doesn't want to deal with the infrastructure. So we try and give an easy Pythonic way of creating that infrastructure for them. And often as well, we know so many of our customers, say no offense to AWS, they say that they don't want to use a bespoke cloud tool because then they get trapped in and then that cloud provider can just rack up the price. And that is why we provide an open source version of what we have to say you can build everything in the library, but it's not going to be unique to us. We give you a Docker image that you can deploy anywhere in a very conventional way so that you're not fully tied in. So yeah, we'll see how that goes.
Cool. All right, thank you. With that, what we'll do is we'll wrap up the talks, but definitely not the night. You're free to stick around, have another drink, chat to people. I don't know if Paul or Uroš have to shoot off, but if not, you might have questions you wanted to ask them that you didn't necessarily want to say in front of everyone. And if it was, I don't know, either too sophisticated or what, too stupid in your own. No question is too stupid, by the way. So yeah, please, grab us and have a chat and enjoy the rest of your evening. Remember, 28th of March for the next one. Big round of applause for Paul and Uroš.